Yes, it seems to be recording even if the storage is full. That's good. So hi and welcome everyone to Jfokus Brown Bag Lunch. This is the 22nd brown bag we actually are doing. So we have been doing this for a while now. I'm really happy to see that so many people joined for this meeting. So as you saw, I started the recording. So the talk will be recorded, but we will not record the Q&A after the talk. So you are all free to ask stupid question. At least it won't be on tape. So I'm Mattias Karlsson, and then we have Niklas Finne. Hey Niklas, and Enno. Hey Enno, that helps me with the moderating and facilitation of the Zoom meeting. Enno, what did I forget? I always forget something.
I think everything's there, so.
Good enough, at least.
Good enough.
Yeah, so with that said, I will leave over to Natan for today's presentation. Welcome, and please do your own introduction.
Thank you very much, Mattias. So let me just share the screen. Hope everyone can see the screen well.
Looks good.
Good. So welcome everyone. My name is Natan Silnitsky, and I'm a backend infrastructure developer at Wix.com. And in this talk, you will see how we can create a distributed event-driven system that is comprised of microservices that are implemented in multiple language and tech stacks like Scala, Java, but also Node.js and Python. And this system will be fault tolerant with high throughput and low latency. And we'll see how we can achieve this by using Kafka, Kubernetes, and gRPC. So first, a few words about Wix. So Wix is a website building platform that also allows you to manage your online presence and business. We have more than 200 million registered users from 190 countries, and 5% of all internet websites run on Wix. And the system of Wix comprises around 2,000 microservices with some of them are with event-driven flows, like when the site is published, this event is consumed by a lot of services, including vertical services like stores and bookings and restaurants that need to process information on such updates. And while most of our services are in Scala, with a few lines of Java here and there, we also have a lot of Node.js services and a few Python as well. And regarding our Kafka usage, we produce, these microservices produce around 1.7 billion Kafka messages per day. And we really need to have these, this flow managed successfully, be performant, fault tolerant, and support all these tech stacks that I mentioned. So we're going to do a short intro on event-driven programming with Kafka. And we'll see how we can gain good performance with Greyhound, which is Kafka library that we developed in-house and open source. And we'll see how we can achieve fault tolerance by using Greyhound and Kubernetes as well, and how we can support all these different languages using Kubernetes and gRPC. So the classic request-reply style of communication, we have two microservices here, the ecom catalog service and site installed application service. And here the ecom catalog is serving as a client who is requesting from the server some information. In this case, what is the newly installed application. So these two services are now more coupled because of this request-reply communication. And what if the network becomes unreliable? So in this case, ecom catalog service will need to implement some ad hoc retry mechanism to make sure that the request eventually succeeds. Side app service can be down momentarily, and then ecom service doesn't have anyone to talk to. And also, let's remember that we have a big ecosystem of microservices here. So This means that this request could be part of a bigger chain of requests, and we can have a bigger impact in case of failure, where this apps service is a bottleneck for all of the other services, and we can have failures and higher latencies. So one possible way to mitigate this is to introduce a broker between the services, and the services then act as a producer and consumer of messages or events. And brokers can actually allow us to gain better resiliency and availability. Usually is a big cluster of brokers that manage these messages, and all the data is replicated among multiple brokers. And so we gain a better resilience. And now these two services are actually completely decoupled from each other. All they need to know is how to communicate with the broker and produce the message and consume it. So they are not much less dependent on one another. And specifically, if we look at the Kafka broker, then messages are produced to some specific topic, in this case, side apps. And this topic is divided into partitions. And partitions are the scaling unit for Kafka, and messages are written sequentially and appended. It's like each partition is like a log, a commit log, where you just, like a commit log, we just append more messages at the end. So it has a better performance than traditional message queues like RabbitMQ in terms of writing and reading from these partitions. And here we can see an example of an event producer that produces a message to the topic, and you can see it's appended at the end. And here we have a consumer that actually will consume the message in their own pace. They could have multiple consumers consuming at different parts of the partition, each having their own pointer. And once they finish processing this message, they will commit it and start the next one. So it's not like messages are actually removed from the queue, like in queues. Kafka just has bookkeeping for each consumer what is the last commit that they wrote, and they can start off from there if there's a restart. And by using this concept of partitions, it's really, really easy to scale up. We just add more and more partitions as needed, and Kafka can easily handle that. Now, at Wix, we decided that we're not going to use the Kafka Java SDK as is. We're going to wrap it with our own library. So we wrap both the Kafka producer and the Kafka consumer. And we call this library Greyhound, and we actually open source it, so it's available to everyone, to the entire community. And the idea is to first simplify the API, have a more declarative style API, you just provide a message handler, as we say, with basically a lambda to process the message. And we also have in Greyhound a lot of additional features. So I'm going to talk about most of them in the upcoming slides. So we have parallel consumption of messages, really easily set up. Various consumer retry strategies, a resilient producer that makes producing fault-tolerant, context propagation to propagate user request context around all the microservices through Kafka, matrix reporting, and also a batch consumer for increased throughput in some cases that we will open source very soon. So we have a basic abstraction layer for message processing, for event-driven style of work. And this is used all throughout Wix. Almost all our 2,000 microservices have some kind of interaction with Kafka. So because we have Greyhound, it's really easy to change stuff for all of these services at once, fix bugs, and change implementations as we see fit. Okay, so we want to jump right in and talk about how we can actually achieve good performance for our event-driven style system by using Kafka and Greyhound. So we have our service, and it utilizes a Greyhound consumer. And this consumer then requires from the service to provide a message handler. And this message handler will actually is the code that is required to process the messages that are being consumed from the various topic partitions. Now, if you want to do this fast, how can we achieve that? Well, basically, all the partitions that are assigned to this service instance, we can consume from them in parallel. So Greyhound Consumer utilizes a Scala 0 library, which is a library that specializes in highly concurrent and asynchronous programming. And it will actually have a worker for each partition that is run on a separate fiber. And these fibers, you can think about them as lightweight threads. We have Project Loom in the JVM that also is trying to work about having run virtual threads of fibers. And so these messages on each fiber, the worker gets the message to internal queue and then processes them one by one from the queue. Now, with the power of fibers is that it's really, really cheap to do context switch between them. And you really don't need a lot of JVM threads here. And also the memory usage is usually much, much lower, at least initially, than with the JVM thread. Okay, so let's see an example with a real use case. Let's say we have a topic that we set up with 80 partitions. And the message processing characteristics for this topic is non-blocking I/O. So we utilize Netty gRPC client. And so we don't really need a lot of CPU. We just do a lot of I/O. And it's non-blocking. And the response latency is around 100 milliseconds. So that means that we can, at maximum throughput, get to 800 messages per second, because 100 milliseconds means for each partition sequentially, we'll process in 1 second 10 messages. But because we have 80 partitions, we can get up to 800 messages per second in the ideal case. Now, if you use the Kafka regular SDK, in the naive implementation, if we want to get this parallelism, we will have to spin up 80 Kafka consumers because they are not thread safe. So each of them has to be run on its own thread, with its own thread. And this way, we will get the amount of parallelism that we want and the throughput that we want, but it's really, really not resource efficient. So you can maybe create your own kind of thread pool and submit messages to it. But Greyhound already does that, and it does that really efficiently with the 80 ZIO fibers that I mentioned earlier, running on a very small thread pool. So we get the maximum amount of throughput that is possible with Kafka with a very low resource footprint. And because ZIO is asynchronous from conceptually, it's designed as completely asynchronously, all these fibers are really going to be suspended, and the threads are not going to actually be used because we're dealing with non-blocking I/O, and that's the reason we can have a very small thread pool. Okay, cool. So let's switch to fault tolerance. How can we achieve complete fault tolerance in our microservices? We saw earlier that with request reply style, it's going to be quite tricky, and there are ways to mitigate it. But with the event-driven style, with Kafka, Greyhound, and Kubernetes, we can really achieve almost 100% reliability rate. So here we have, for example, renew subscription topic, and we have our Greyhound consumer. And let's say that the message handler failed to process the message. So with Greyhound, you can actually specify to have retries done with increasing intervals after 1 second, after 1 minute, after 1 hour, in case of processing failures. And how it works behind the scenes is we have a retry producer that will produce the message to the retry topic according to the intervals that you set. So we have retry 0 that will process, the consumer will process the message after 1 second. And if there's a failure here, the retry producer inside the Greyhound consumer will produce the message to the second retry topic, retry 1, which will then process the message after 1 minute. And so this means actually non-blocking retry. We also have a blocking flavor that will continuously try to process the same message in order to have continued to keep order. So if you look at the complete use case, we have the Wix payment service that is in charge of payment subscription renewals. So we have an external job scheduler that schedules renewal jobs for Wix payment service. So the first thing the service will do, it will produce the message to Kafka. And if the message is successfully produced to Kafka, we know that it will eventually be consumed because we have a Greyhound consumer with the retries on failure. So the job scheduler does not need to worry about rescheduling in case of failure. It can fire and forget. But what happens if the producer actually fails to write to Kafka? Maybe there's a specific network issue between this Kubernetes pod and the Kafka broker, or this Kafka broker is acting badly for some reason. We don't want to lose any messages, right? So for that, Greyhound offers a resilient producer that actually first produces the messages to disks, saves the messages to disk, and only then it produces the message to Kafka. And of course, it will retry in case of failures. So here again, we can make sure that messages will eventually be produced to Kafka. Now, usually our services, if we're in the cloud, are running on Kubernetes in these days. And so each Kubernetes pod is assigned a volume, a mounted volume on the disk. So the messages of the resilient producer are saved on this volume. But if the pod is killed, replaced, then this volume is no longer available for the next scheduled pod. So potentially we can lose messages. So what we did in order, because the volume is not available anymore. So what we did in order to mitigate this is to utilize the power of Kubernetes DaemonSet deployments. With DaemonSet, you get special pod that is only deployed once per Kubernetes node or host, and it has access to all of the volume or disk of this node. So we have now a separate deployment for all of our Kubernetes nodes with a service we call Scavenger that can now access the messages that are being saved in order to be produced to Kafka. And if a pod is killed, then the Scavenger service can actually notice this, and it will then take these messages and flush them out to Kafka. So even though the pod is not completely resilient, our entire solution is completely resilient, even for Kubernetes limitations. And one last note here is that we want to have the Scavenger be with as small footprint as possible, because with DaemonSet pods in Kubernetes, you want them to have as low memory and CPU usage as possible, because you don't want to take up too much of the resources for the regularly scheduled pods in this Kubernetes node. So the Scavenger really just puts the messages to S3, and then a completely regular service will then take messages from S3 and produce them to Kafka. So it's important when you're using DaemonSet pods to have as less work as possible. Cool. So the third act for this talk is about multi-language, multi-tech stack environment in production. It's very popular these days to work with more than one language. So how can we get across-the-board event-driven programming with various kinds of languages? So we'll see how to utilize it with Kubernetes and gRPC. So our two main languages are Scala Java and Node.js. And talked about Greyhound and what it has to offer. So the team that develops the Node.js infrastructure developed their own Greyhound version for Greyhound. But there's an issue here that for each feature that we introduce to Greyhound, we also need to put it completely from scratch in Node.js, in JavaScript or TypeScript in Greyhound. So that's duplicate work. And usually Greyhound only had partial implementations. It's not the main focus of the Node.js platform. And so they usually just played catch up. And also the Kafka library for Node.js is not very, very reliable. And it's usually lagging behind the JDK library for Kafka. So it's really not an optimal solution. So we started searching for alternative solutions for non-JVM language services. So first idea was to use GraalVM. So we experimented with that. The Node.js service team experimented, and it saw that it was not mature enough for all the multi-threading and all of the needs that are actually part of Greyhound here. So they decided to drop that. And the second experiment that actually worked here is actually to have Greyhound as a sidecar service alongside the Node.js application. So the Node.js application can communicate with gRPC with the Greyhound service and request to produce messages as a client. And the Node.js service can also act as a service that accepts new incoming messages from the Greyhound consumer. And the reason that we chose gRPC is, first, gRPC is what we use for the request reply style in our microservices communication. And the fact that it utilizes a protobuf interface definition language means that it's really easy to implement in various kinds of languages. So the Greyhound sidecar service is implemented with Scala, but you can take this protobuf and implement client and service with Node.js and also with Python. Like I mentioned before, we also had Python services. So it was really easy for them to also implement the contract using gRPC and protobuf. So how does the sidecar work? I keep mentioning a sidecar. So let's see how Kubernetes pod is actually made up. So we have multiple pods in the Kubernetes node or host, and each pod has multiple Docker containers potentially, and each of them will get assigned a disk volume as well. So how the Greyhound sidecar comes into this picture is that on each deployment of Node.js applications or Python applications, they also get deployed with the Greyhound sidecar service. And that means that they can all easily enjoy the Greyhound services no matter which language they are developing it, and just get it seamlessly by using regular Kubernetes standard deployments. Now, when you use an additional sidecar container in each pod, there is a potential memory issue, especially when we use a JVM application. What we notice is that JVM applications tend to be bigger in their memory needs than Node.js ones. So their optimization for this, for certain use cases at Wix, we decided to have the Greyhound service be actually a DaemonSet pod that has the same single deployment for each Kubernetes host. And the use case that we actually switched to a DaemonSet for Greyhound is when we have these applications that are actually just one single function. So we have a sort of a serverless implementation at Wix where it's really easy to deploy a single function written in JavaScript, TypeScript, and then it makes a lot more sense to actually have these functions have multiple functions use the same Greyhound pod instead of having each function work with a full-blown Greyhound sidecar, because that's really inefficient memory-wise. So if you take a comparison of putting the Greyhound functionality in a sidecar container or DaemonSet, we can see that with the sidecar we have gain a simpler design where you don't need to keep a lot of state. With DaemonSet, it's a bit more complex. You need to actually handle all the state of the multiple tenants that are part of this Kubernetes node. Now, with the sidecar container, the lifecycle of the application and sidecar is pretty much in sync. You can really sync it quite easily. But with DaemonSet, if the DaemonSet is down, even for GA, it means that all the various node applications functions currently could not access Kafka, basically. And if there's a failure on the sidecar, you only affect one application. But if there's a failure on DaemonSet, you will affect a lot more consumers. And of course, the flip side here is that using a sidecar means a greater memory overhead. So of course, with DaemonSet, it's much easier on much less strain. Good. So here, another mitigation that we did is to actually extract the Greyhound service producer side to its own clustered service in order to avoid any downtime related to producing. Because if the function currently needs to produce a message, we don't want the fact that the DaemonSet pod is currently restarted to affect it. We want this to be highly available. So we need more than one instance. We need a cluster, like with regular Kubernetes deployments, replica sets. And but with consuming, it's not a too big deal if we have a couple of seconds where we don't have the ability to consume, because we can maybe a little lag will develop, but we can gain advantage later on. Now, there is an additional network hop when you use the Greyhound producer service instead of actually doing a gRPC call inside the host. But because this is inside the same data center, it's usually very, very fast, a few milliseconds to get to a different Kubernetes host inside a data center. So it's pretty negligible. So to summarize, we use Kubernetes flexibility to deploy Greyhound producers and consumers in different patterns in order to comply with different requirements and constraints, like production costs and the need for resilience and how Kubernetes works and stuff like that. So Wix harnesses Kafka, Kubernetes, and gRPC to achieve a polyglot, highly available, resilient, fault-tolerant, scalable, highly performant, event-driven distributed system with growing scale. And like I said, the Greyhound library is actually open source, so you can check it out on this link at github.com/wix/greyhound with all the features I mentioned that are available in the open source version as well. So thank you very much. And you can see all the links I put and all the slides on SlideShare in this link. And you can also follow me on Medium and Twitter to get updates on what we're up to in the data streams team at Wix, in charge of event-driven data streaming and all things related to Kafka and other software engineering practices that I write about as well. And you can also check out my website at natansil.com to check out previous talks I gave at conferences and meetups. And thanks again. I would gladly answer any questions if you may have them.
Thank you, Nathan. I'm jumping in instead of Matthias as he had to leave for a while. I will stop the recording and then we'll take questions.